So we got a couple things with derivatives. This first one is just like we've been doing. The first thing to do before I find the derivative of this, and we're not worried about finding the tangent line yet, but if I wanted to clean this up in order to start finding the derivative, I'm going to have to do this. I think you all are okay with up to that point. Agree? All right. So then if I take the derivative, y prime, because everything's all parted out, we can, we're just working on that, some notes. If we take the derivative of this, bring this down front, that gives me a 9x, and then I subtract 1 from there. That's easy. And then bring this straight down, so I get plus 1/2 x. And then I subtract 1, which is the same thing as 2 over 2, so I get then this. Okay? So that's basically the derivative. As of this class, I'm fine if you leave it like that. But realize in future math classes, they probably want you to clean this up a little bit to make it become something like this. So these are the same. It's just cleaned up in the purple on the bottom, or I believe it's purple. Okay, so again, if you can get to the red in here, I'm happy. Here you go. Here you go. So that's what we've been doing so far. I didn't say let's find the let's find the tangent equation at this point. We're just taking the derivative of it. So we have to realize that all the derivative does is the derivative will allow us to figure out what the instantaneous point of tangency would be at a certain point. Oh, thank you much. Does that make sense? All right. Can I move off this? So again, if you get to the red in here, you're going to get it totally right. There's no reason to go any further in here. Future math classes will want you to realize that this portion here wants to move back downstairs and then turn it back into a radical. Okay? But let's go down to the next problem. And we want to find y prime. We want to find the derivative of this. Now, the problem with finding the derivative of this, if I didn't have the parentheses and the quantity raised to the 4th power, I could find the inside derivative real easily, saying it's 4x plus 3. But I threw a little bit of a wrench into the game. So in order to find the derivative, first thing I'm going to do is I'm going to do the derivative of the outside. So I'm going to bring that down, subtract 1 from it. So I get a 4, and then I get 2x squared plus 3x plus 5 raised to the 3rd. Okay? Then I have to take the derivative of just the inside. So then that's going to be times 4x plus 3. So this entire thing is the derivative. Okay? So how that works is you do the derivative of the outside. So you lower the exponent by 1. And bring whatever the exponent is down front, lower by 1, and then you multiply by what's inside. A lot of times, this is done this way.
Why can't you take the 4 out to all of them?
I'm going to show you what. Well, I could go 2x squared plus 3x plus 5, multiply it times itself by huge foiling methods.
But it's irritating.
I mean, you're talking about something that's going to be all the way across your paper and then some. Okay? So a lot of times this type of problem is done this way. They'll say, let u equal, in this case, 2x squared plus 3x plus 5. Okay? And so that means that if you replaced u on this, you'd get y equals u to the 4th. Take the derivative of u to the 4th. You get 4u to the 3rd. But then you have to realize you have to figure out the derivative of the inside. So you could plug u back in, but then you have to take the derivative of the outside. So this is a process that they would do in future math courses. But for the most part, when you're going through this type of problem, if you had a complex problem, so complex raised to an exponent, in order to do the derivative, you bring the exponent down front times the complex, and then the exponent minus 1, and then it's times the derivative of the complex. So it's just you're doing it by part, okay? And that's kind of a real wordy kind of component. But the question that was asked before is a legitimate question. So if you wanted to take our original problem, because it's raised to the 4th power, it's the same thing as saying this. And if you were to multiply that whole thing out, which is just ridiculous, that's a ridiculous amount of math. I mean, if you want to do it, I welcome you to do it, but you might not have enough time this month to finish that problem just because there's an awful lot. Okay, so I'm on the back side. So I have y equals x squared minus 4x, and it's raised to the 6th power. Okay? If I just had the x squared minus 4x, derivative all day is 2x minus 4. That's relatively simple. But we have this outside thing. So in order to do the derivative of it, I'm going to bring the 6 out front times what was inside the parentheses, lower the exponent by 1, and then multiply it times the derivative of the inside, and that becomes the entire derivative. Okay, so you're doing a derivative compounded with a derivative. Does that make sense, my friends? More than one person? Make sense? Appreciate you. And again, friends, you don't have to start using the algebra to get it all cleaned up. Just leave it messy. Okay? Can I move off this one? No? Is there a no? I thought I heard a no, but I might be hearing stuff. Okay, so let's add to this one. Let's add to this one we just did. What is tangent equation at x equals 1? Okay, so this is kind of now doing what we were doing. Now we're going to try and figure out a tangent equation at the x value 1. So, friends, if I take this 1 right here and I plug it into my derivative, what would that find me? If I were to plug that 1 in, what does this find me? Thoughts? Slope. Very good. Good job. Okay, so if I take that 1 and I wanted to find the slope, this is going to find the slope of the tangent line. So then just go through and do the math. 1 squared is 1. 1 minus 4, so that's going to give me negative 3 to the 5th. And of course I chose, it's going to be ugly. 2 minus 4. 3 to the 5th. Someone have a calculator? They can do 3 to the 5th power. It's going to be negative.
Wait, 3 to the 5th power.
Yeah, 3 to the 5th power.
243.
243, thank you. And then I need help with math. What is 12 times 243?
2,916.
2,916. So that's what our slope is going to be. That's pretty steep. I go up 2,916 for every one move to the right. Okay, well, it still works. All right, what happens if I take this and I plug it into our original? What does that find me? Yeah, this is going to be 1 comma something. So this is going to find us the point of tangency. Point of tangent. All right, so if I plug 1 into this, I'm going to get 1 squared minus 4 times 1 raised to the 6th power. So that's going to give me 1 minus 4. Come on, stirrup. 1 minus 4 raised to the 6th. So I need negative 3 to the 6th power. Yikes. What is 3 to the 6th power? Or 9 to the 3rd? 729? No.
Yes,
Is it really?
Yeah.
I have, dude. I need to take a nap. I don't know how this melon of mine did that kind of mental math that quickly. I am so sorry. Okay. So our line of best fit, our tangent line is going to be y minus 729. Our slope is 2916. X minus 1. So this is the linear equation that would be tangent to the original equation at 1. And I might be asking for trouble to do this. But I just want to see what Desmos has this looking for, because that slope is enormous. Can you imagine if you're in algebra 1 and you have a slope of 29/16? So we're going to go up 29/16 and then write 1. Good luck graphing it. Oh, okay. Can I borrow a pencil real quick? Thanks, brother. Let's see. So I'm going to do this. Graph that. I have the point 1 comma 729. Thanks, sir. Oh my gosh. I'm going to ask for trouble. I'm sorry. I'm going at this on a whim. All right. If I graph my... I'm going to graph this. Let's see. How do I want to do this? I'm going to go y equals x squared minus 4x. Raise that to the 6th power. Okay, so that's basically why it's so steep. I mean, that creates this unbelievable double root. I have no idea if there's even more to this than that. All right, and then I'm going to plot the point on the table, 1 comma and 729. Okay, so now I'm going to zoom here. Let's make that a little nicer, bigger. All right, so that's the point of tangency of that monstrosity graph. I mean, if I zoom out, basically I'm looking at, looks like a whole bunch of vertical lines, but at some point this is going to come together in between them. It's like, dude, you just have a solid line stirrup. Just go with the original. Okay. And then if I'm going to graph this, I'm going to graph y minus 729 equals 2916 x minus 1. And I'm going to change this color. Okay. So here's the hard thing. That appears to be the exact same as that. But why is it so close? I mean, if I look at this original equation, that looks pretty close to a vertical line. Okay, it's not quite vertical, obviously this looks like a vertical line. The reason this looks like a vertical line is because I'm going up 2,916 vertical units before I go to the right 1 unit. And of course, if we, zoom into this all day long, I don't even know if we're going to be able to see a separation between the two. No, it's just not going to happen. So that's kind of bigger meat and potatoes on this problem, I think. Okay, so let's get away from Desmos, because though it could be our friend, it could also be a little hurtful to think about that. All right, the last problem I want to look at is we have y equals 3, and then I have the third root of x squared minus 3x plus 1. So I want to clean this up a little bit. I have to realize that the third root of x is the same thing as x to the 1/3 power. So I'm going to change this to 3 parentheses x squared minus 3x plus 1. If that's raised entirely to the 1/3 power, that's going to take place. Okay. Are you ready for the derivative? Okay. The nice thing, this 3 is just coming along to the right. This is basically like I factored a 3 out. Okay. Now I'm going to put square brackets. I'm going to go 1/3 times x squared minus 3x plus 1.
Wouldn't the 1/3 cancel with 3 alpha?
We will. It's going to get there. I like your thought. I'm going to subtract 1 from this, so I'm subtracting 3/3 from that. So that's going to be negative 2/3. Then times the derivative of the inside. The derivative of the inside is this. And I like the forward thinking. Will this cancel this? And the answer is 100% yes. If I got down to this answer here, I think you've done some beautiful work. If you truly wanted to clean this up, this cleaned up version of this is going to look like this. 2x minus 3 over the third root of x squared minus 3x plus 1. Keep that in parentheses, squared. This is the derivative. And there ain't no way I'm going to go try and fathom what that would be at x equals 1. Okay? Yikes. Whew. Okay. Okay? Can I give you some stuff to practice?
Yeah.
Okay. I kind of sort of planned something. And I enjoy the fact that you guys let me go about my madness with you. No one started screaming at me yet, so I appreciate that. It's eventually going to happen. You suck as a teacher. What? I hate you. Okay. All right. So I would like us to work on our worksheet 4.5. Okay. And I'd like you to do 2, 7, 8, and 10 is, I'm going to put a question mark with it. Okay. Basically what you're going to do with number 10 is you're going to take the first derivative of it, and then you're going to plug 100 in at that point. Okay. Cool. So try that. What am I supposed to do? Take attendance. Thanks.